In front of a mirror, some objects produce images that can be superimposed on themselves. Object and reflection are identical. In contrast, other images are non-superimposable. The objects that are not identical to their mirror images are called chiral and are said to have chirality. Nature is full of chiral molecules, which can exist in the two forms. A chiral molecule and its mirror image are called enantiomers. The two enantiomers of a molecule scatter polarized light differently. A solution containing one enantiomer rotates it to the left. This is called the L form. The other chiral molecule rotates the light to the right. This is called the D form. Whether a chiral molecule is L or D is more important than it may seem. The generation of quartz crystals depends on this, for example. And so does being able to assemble materials of the future, such as carbon nanotubes. The liquid crystal screens on which you can watch television or surf the internet also depend on chirality. Whether a volatile molecule smells of pine or orange is also dependent on whether the L or D form reaches our nose. For the same reason, a molecule may make food taste sweet or bitter, and a substance may or may not be an effective medicine. These things happen because the receptors in our nose, tongue, and the cells of our body in general are also chiral and react in distinct ways depending on the form of the enantiomer they encounter. This means that we, as human beings, also have chirality. For example, the sugars in our genetic material are D forms, and our proteins are made up of the L form of molecules called amino acids. Even our anatomy is chiral. We only need to look in a mirror to be aware of this. Given that the two enantiomers of a molecule may cause very distinct reactions in our cells, and that many of these molecules can be used as medicines, it is important for scientists to separate them when they are found mixed together. But the molecules are thousands of millions of times smaller than a speck of dust, so how do they do it? Let's imagine that these two gloves are the two chiral forms of the molecule, and that only one of them is of interest. To trap it, you need a gold surface with a layer containing molecules that acts as hooks. In other words, these molecules only enable the adherence of the chiral form we are looking for, as if they were hands that only fit in the glove we are interested in. The enantiomers of interest remain trapped in an organized form on the surface. It is only possible to see them using sophisticated microscopes with probes able to determine molecule by molecule if they have linked correctly to the surface. Scientists can also make stamps that can be used to mark the surfaces so that they have the ability to attract different chiral molecules. These create patterns of varied designs, which, in contact with the solution of chiral molecules, specifically attract either the L or D form. In this way, the enantiomer of interest is retained, accumulating on the area marked by the stamp. It grows on the surface, forming crystals, from which drugs and other very specific products can be synthesized.